Welcome to the VHDL Design and Modeling of Digital Systems course, Processes. The process itself is considered a concurrent statement that contains sequential statements. As such, it does not matter in what order which the processes are defined within an architecture body. Here's the syntax for a process statement. An optional process label, process, and optionally within parentheses the sensitivity list, then we could have 0 or more process declarative items, and we'll talk more about those later, followed by the keyword begin, followed by the sequential statements. Now, the order in which the sequential statements show up within the process obviously is important, followed by end process, then the optional process label. The signal list, if any, following the keyword process is called the sensitivity list. That's what's inside the parentheses. If one or more of the signals within a sensitivity list changes in value, in other words, experiences an event, then the process resumes execution at the beginning of the process. Here we have a screen capture of two processes that are equivalent. In the first process, it says process, and the signal list or sensitivity list consists of a single signal called random signal, followed by begin report random signal had an event. The second process, which again is equivalent, has no sensitivity list, and it has the same report statement, and following the report statement is a wait on signal, random signal, and remembering that wait on is wait on sensitivity list. Now, one thing I want to call to your attention here is that both of these are equivalent, and yet the wait on random signal is at the end of the process. So you can see here that since they both behave the same, even if random signal does not experience an event at all upon in our first simulation time at time 0, both processes will execute, starting with the first line, which is the report signal. I point this out because that's the way the process behaves in the language. It's the sensitivity list is basically meant to trigger what happens once it hits the implicit wait at the end of the process. We say implicit because when you have a sensitivity list, in this case random signal, it's equivalent to a wait on random signal at the end of the process. Signal assignments made within a process take effect only when the process suspends, either because of an explicit wait statement or because of an implicit wait statement that happens at the end of a process, in other words, one with a sensitivity list. This process here describes what I'm talking about. The process begins, random signal is assigned to 1, then random signal is assigned to 0, then there's a wait for 10 nanoseconds. Now, because the process only suspends when it hits the wait, that's when the signal assignment takes place. This does not cause a glitch, as some people seem to think. It does not, because the random signal is assigned twice, but it's only the second one that's actually ever seen outside of the process. So in this example here, random signal never changes from the value of 0. A couple final notes on processes in general. A process without a sensitivity list or a wait statement never suspends. Also, a process is said to be passive if neither it nor any procedure that it causes a signal assignment. A passive process may be contained within a entity statement of a entity declaration. Now we're going to talk about combinatorial processes. The outputs of a combinatorial, also known as a combinational process, are strictly a function of its inputs. The process contains no memory or feedback within itself. All inputs in a combinatorial process should be contained within the sensitivity list of the process, or else we might create an unintentional transparent latch. Also, a combinational process should not make any assignments to any of the signals that are in the sensitivity list. If it did, the process would cause itself to be re-executed after it reached the end of the process. This may result in unintended effects. All the output signals should have at least one assignment, regardless of the execution path, or else again we might create an unintentional transparent latch. Here's an example of a combinatorial process. Random signal 2, random signal 3. Those are the two signals as part of the sensitivity list. The first thing it does is assign random signal 1, which is the output from this process, to a specific value, in this case 0. Then we execute an if-then statement. If random signal 2 is 1, then random signal 1 is assigned the inverted value of random signal 3. Now, this follows all the rules of a combinatorial process. The outputs of this process are strictly a function of its inputs. The process contains no memory or feedback within itself. All of the inputs of the process are contained in the sensitivity list. Also, the process does not make any assignments to any of the signals that are in the sensitivity list. And the output signal, namely random signal 1, has at least one assignment which occurs regardless of the execution path that the process might take. There are times where we may want to intentionally create a transparent latch. A transparent latch is created when the execution path does not always cause a signal assignment. Here's an example of a transparent latch. In this case, a process with sensitivity list includes latch and enable and random signal 2. If latch enable is 1, then random signal 1 is assigned with whatever is in random signal 2. And that assignment happens for the duration that latch enable is equal to 1. Now, if latch enable ever goes to the value other than 1, then the signal assignment does not occur. And in this case, the execution path would not result in a signal assignment. One thing we run into quite often in VHDL is unintentionally creating latches. Unintentional transparent latches can be avoided by following these two simple rules. The first, list all inputs into a combinatorial process in the process sensitivity list. And the second is, make sure that each output of the process must be set during the execution process, regardless of the execution path. The best approach is to set all outputs of the process at the beginning of the process to their default values, and we will be showing examples of that. Now we're going to look at sequential processes. A sequential, or sometimes called the clock process, is a process whose execution is resumed based on a specific change, like the rising edge or the falling edge of a specific signal, like a clock. The clock is always listed in the sensitivity list of a sequential process. The sequential process may optionally contain a reset signal and or an enable signal. The reset signal is used to drive the output to a known state upon an external command. An optional enable signal might be used to select upon which clock edges that the process inputs are clocked onto its outputs. A pure sequential process is one whose inputs are clocked onto the process's outputs. A pure sequential process does not contain any combinatorial logic. Here's an example of a sequential process. The keyword process followed by clock in parentheses. Clock in parentheses is the sensitivity list, single signal clock, and then begin. If clock event and clock equals 1, what that's doing there is first clock event is saying if there is a change in value of clock, and if that value is now 1, in other words, a rising edge of clock, then we execute the signal assignment. The signal assignment is we take the value of count, we're adding 1 to it, and then we're assigning it back to count. Now, even though the count is an input to this equation, it's not part of the sensitivity list, because the only thing that we care about in the sensitivity list is, in the case of a basic sequential logic or sequential process, is the signal count. Now, strictly speaking, this is not a pure sequential process because count plus 1 is basically combinatorial logic. To make the sequential process a pure sequential process, we have to take out the combinatorial logic, which is what we've done here. Now the signal assignment is current count is assigned with what's currently in, or what's presently in, the value of next count. The first line there, next count is equal to, or is assigned with the value of current count plus 1. That's basically a concurrent signal assignment, so that when current count changes value, 1 is added to it, and that's assigned to the signal next count. Here we're adding a asynchronous reset to our sequential logic. Since it's asynchronous, we have to make reset, the reset signal, part of the sensitivity list. As you see, it says if reset is equal to 1, then current count is assigned the value 0. Else if clock event and clock equals 1, in other words, a rising edge of the clock, then we're going to assign current count whatever is in the signal next count. If we change the reset from asynchronous to synchronous, we're basically placing it after the rising edge logic. And also we remove reset from the sensitivity list, since now the only time we will look at the reset signal is when we are experiencing a positive edge of the clock. Now, something else I'd like to point out as well is, unless you know that you must have an asynchronous reset, in my opinion, it's best to have all your resets be synchronous. The reason I do not like asynchronous resets is when it comes down to it, you do not know exactly when the logic goes into reset, or that when it comes out. That might be an issue if you come out or you remove your reset signal as the clock edge is happening. Now, since you can possibly have multiple bits changing simultaneously, you might end up with some sort of strange transient condition that would happen very infrequently, but statistically is still possible. One more change I'm making here is basically adding a clock enable, which is done synchronously. So still the only signal in the sensitivity list of our sequential process is the signal clock. Here we also still have the synchronous reset, so if we experience a rising clock edge, we check to see if reset is equal to 1. If so, we assign current count to 0. Else, if clock enable is 1, in other words, we're enabling the clock, then we assign current count to next count. Now, the reason I write it specifically this way is because the flip-flop control priority of Xilinx parts, especially the Spartan 6, most likely others as well, follow this priority. So basically I'm taking advantage to, or how the Xilinx flip-flops support control priority. If I were to have the reset swapped around with the clock enable or change it around such that I might end up with logic that would be implementable but would not be optimal. Also, as a matter of personal preference, I prefer using the function called rising edge on clock. Now, functions are subprograms we haven't covered yet, and rising edge is basically a function defined in the IEEE library, and the package is std_logic_1164. The reason I like it is because it basically it strips off strength, which is something we haven't covered yet, but also it makes it more readable as far as the code itself. You can see, if rising edge, you can deduce what that function's doing. At this time I want to put forth a methodology which at first, for some of you folks who already have some familiarity with VHDL, might chafe against. I know I did when I first encountered it, but have since come to use it and love it. Anyway, it's called the two-process method, which was originally developed, put forth by Jerry Geisler of CTH Geisler Research. Basically, he breaks up RTL, register transfer logic designs, as being performed by two processes, one combinatorial process and one sequential process. The one combinatorial process should calculate the next values, those that are fed into the input of the sequential process, as a function of the current values, those taken from the output of the sequential process, and conceivably external inputs. From a pragmatic standpoint, combinatorial processes should be separated into functionally related, i.e. where different outputs may be a function of the same set of inputs. Also, there's nothing oftentimes that says that we can't implement some of these combinatorial processes in concurrent statements, especially when we're only looking to create one signal. So a concurrent statement might be the most appropriate. The one sequential process should clock the next values, which come from the output of the combinatorial process, into the current values, which are fed into the input of the combinatorial process. From a pragmatic standpoint, a different sequential process should probably exist for logic that uses different clocks, or clock enables, or resets, or modes of resets, like asynchronous versus synchronous.